Hi guys, welcome to another Learn Electronics Repair video. This video we're going to learn all about inductors. All you need to know about inductors to fix things. First of all, let's have a look at the schematic symbols for an inductor. So the main symbols you will find for an inductor are this one, or sometimes drawn as this. These are fixed inductors. You will also find with or without the coil or the bumps, yeah. This one. This one. And this one. Okay. To understand why the symbol looks like this, we need to understand what an inductor is. And basically, an inductor is just a piece of wire wrapped round and around some sort of former. The former could just be a piece of plastic or paper even, or it could be, and more commonly, a magnetic material. It could be a solid metal bar or laminations of solid metal, or it can often be a substance called ferrite, which is basically a mixture of ceramic and iron dust or particles. Now you know that, you can probably understand these symbols. So this just represents the coil of wire. Yeah. This one is a coil of wire around a solid metal core. Coil of wire around the ferrite, shows the dashed, yeah, effectively parts or bits of metal. And this one is a variable inductor. You won't find these very often, hardly never, to be quite honest, unless you're working on radio frequency circuits, and then you will come across variable inductors. When you connect a voltage across a coil, the coil initially will try to prevent current flowing through the coil, and it does this by storing the energy and the voltage, if you like, in the magnetic field that is generated when current flows through. So an inductor stores energy, and it stores the energy in its magnetic field. The amount of energy it can store is measured in henries. So we measure inductance, if you like, in henries, and the symbol is a H with a capital H. 1 Henry is quite a large amount of inductance, but you will find circuits with inductors rated in henries. However, in a lot of circuits, the inductance is much lower than that. So commonly, you will find ratings in henries. You will find them in millihenries, which is 1,000th of a henry, and you will find them in microhenries. Usually done with a Greek mu sign, or sometimes you'll find UH. So those are the main ratings you will find for an inductor. Inductors don't have any other type of rating like voltage rating. There will be a maximum current that the inductor can pass, but generally speaking, the henries is the only rating you actually see on an inductor. An inductor can store energy in its magnetic field very quickly, and likewise it can discharge very quickly. This feature is important in many modern circuits where the inductor is used effectively to regulate voltage. Inductors, although they're very simple devices, it's just a coil of wire, they're often very much misunderstood by people. Having said that, really they are quite easy to understand. So I'm going to show you now diagrammatically how an inductor actually works using an analogy of water flow. And if you can understand this, it will give you a lot better idea of how an inductor actually works in a circuit. So in our analogy, we have a pump, a water pump. And the water pump is doing what a water pump does, it's pumping water, okay? And the water is going on the outlet down a pipe, and there's a fork in the pipe, okay? This side of the pipe goes to a very narrow section of pipe, okay? And this will restrict the amount of water that can flow this way. Effectively, if you like, this has resistance to the water. It's a resistor, okay? The other branch of the pipe goes to a water wheel. Okay, and the outlet from the water wheel comes back to here. And this is a closed circuit, so the water then returns back to the pump, ready to go round again. Okay, so that's what we have: pump, water wheel, resistance, a thin bit of pipe. Okay, so now the water wheel is very heavy. So when we first turn this on, the pump will push water out, and when the water gets to this branch in the pipe, it will have to go either one way or the other. Okay. Now the water will flow through the path of least resistance. Initially this water wheel is standing still, so the water that comes into here will fill this chamber and push on the water wheel. But the water wheel takes time to get moving, so most of the water will actually be going down this way and through here and back around to the pump. As this pushes against the water wheel starts to turn, and gradually water will start coming out of here and flowing back around the circuit. Yeah? And this water wheel will speed up. It has inertia, so it resists the flow, but it speeds up faster and faster and faster and faster. And eventually, this water will be running at its full speed, and almost all the water will be going round this way through the water wheel, and very little of it will be flowing this way. What water's in here will practically be standing still. Okay. Now imagine what happens if we turn the pump off. So we've got a tap here and we switch it off. No more water is flowing from the pump, but the water wheel is still rotating, and the water wheel, because of its weight, its inertia, it can't just stop, it has to slow down. So the water wheel starts to slow down, but while it's doing so, water is still coming through this, it's still spinning, and the water now, when it gets to here, it can't go back through the pump because this is switched off, there's no path of flow. So the water now comes back through this way and back into the wheel. Yeah, and this will keep rotating and the water will keep flowing here, and this will restrict the amount of water flowing, so effectively there is friction, resistance, and the water will gradually slow down and eventually it will stop. Okay, it will stop. Now let's have a think about what's happened here, because this is an important fact. When the water was flowing through, this was the point of high pressure. This was the positive end, the highest pressure. If you think this is a battery, this is electricity, so this is the positive end, yeah? And the other end of the water wheel is the negative end, because it's of lower pressure. This starts to speed up and speed up and speed up, and it reaches a point when the pressure difference either side is non-existent practically. This is now going at full tilt, water's flowing very rapidly, and there's basically no difference. So at this point, this is just a piece of wire. It's just passing water freely, yeah? When we switch this off, we know the water wheel continues to spin, but it slows down. So as it's spinning, it's pushing water around this way, yeah? Now, notice the flow of the water is reversed. When we first switched on, it was coming this way. Now it's going that way. The flow of the water through here is still the same direction, but effectively now, this is the positive end, the high pressure, and this is the negative end. You see they've reversed, yeah? And that same thing applies in the electrical circuitry. So when you suddenly interrupt the flow of current through an inductor, the inductor will continue to push current through the load because it has inertia. It has to slow down effectively. The magnetic field has to collapse, yeah? And during that time, the polarity across the inductor reverses. And that has a name, and it's called back EMF. And this can be important in circuits because this reversal of polarity can affect the device that's switching this on and off, especially if that's a transistor, for example. So an inductor will pass current but effectively resist changes in that current. That means basically that an inductor will pass DC, direct current, and it will block AC, which is changing the current, such as reversal of it. Yeah, so that's what an inductor does. The main uses of inductors are as filters, where they will effectively filter out the AC components, and depending on the value of the inductance, that will affect how it passes different frequencies of AC. So they're used as filters. They're used in circuits called VRMs, voltage regulator modules, in particular a circuit called a buck regulator, and they can be used to either reduce or increase a DC voltage. So you can have a DC voltage coming in and the other side of the inductor a lower one, or you can have a DC voltage coming in and the other side of the inductor a higher one. Okay, and that's either called a buck regulator or a boost regulator. The buck reduces the voltage and the boost increases the voltage. This is an interesting topic, and there'll be another all you need to know about buck regulator video later. So we find inductors commonly on power supply circuits, on motherboards, and pretty much any electronic device these days which has multiple voltage rail requirements will find inductors. We also find them commonly in a circuit called power factor correction, which is in larger power supplies, ATX power supplies, and similar power supplies built into TVs, for example. And that's another common use. And again, we'll do a video on power factor correction explaining that one. And the other thing to note with an inductor is that any device with a coil inside it is effectively an inductor. So relays, solenoids, motors, transformers, all these devices are effectively inductors. It's interesting to note that although inductors are measured in henries, the donation on a schematic for an inductor is L. So you'd have our L25, L1. This is just L for inductor, and this is the component number, not the value. The reason for this, H actually is for Joseph Henry, who was one of the pioneering scientists working on inductors, and L is actually after Heinrich Lenz, who was another scientist working on inductors. It was the Honor Lenz. Lenz is the guy, by the way, who gave us the plus and minus sign. Okay. Another good reason, if you like, and why it isn't I, is because I is the symbol for current. Intensity de courant from the French. Okay, so they couldn't use I, so they had to use something else, and they used L, basically to honour Heinrich Lenz. So what do inductors look like? Well, they come in a whole variety of shapes and sizes, really. These are inductors, and we can clearly see the coils of wire. These are transformers, which are a type of inductor. We'll talk about these in another video. And I think that's probably the main ones on this board. There's a smaller one here. So this is an inductor. These are smaller transformers. Inductors can also look like pretty much like a resistor. And the way to determine normally, if you see on this board here, so all the resistors are marked R, R46, R43, R40. So this is not the value, this is just the identification number of that component on the schematic. The capacitors are marked as C. Okay, so we have C27, C26. J for a jumper, just a bit of wire. If you see something that looks like a resistor and it's marked L, that will be an inductor. Let's have a look at a few more inductors. This is a part of a power supply. This has some quite heavy, large inductors on it. There, and there, you can see. So these are inductors. And this is a motherboard. So on here, we can see. These are inductors. These square things, okay. Some more here, different sizes, slightly smaller. Very small one there, or smaller one. That isn't an inductor, it's a little that isn't an inductor, it's just a plastic peg holding that in place. And can we see some small ones on this one? Nothing jumping out at me. Okay, let's have a look at another one. This off a TV, I think. So again, inductor, yeah. This is an inductor, this shape. We see these ones. This effectively is an inductor, yeah. PL, L for inductors. That is actually an inductor. And do we have any more on this one? There's another inductor here, yeah. It's got LPL82. So we've seen that type. Another one here. So those are inductors. Let's find another board. One more to look at. Okay. This will have inductors on it somewhere. Just need to have a look around it a little bit. Yeah, okay. So these are inductors. This oblong shaped one. So you can see they actually come in quite a variety of shapes and sizes. But once you know what they look like, they're not difficult to spot. Normally, the value of an inductor isn't actually marked on the component. If it's marked at all, it'll be on these type. And you can see this one says 1 or 0. This one says 1 or 0 again. Now, that can be, I believe it's confusing because basically 1 or 0 is a 1.0 ohm resistor, if you know anything about resistors. So it's like they use the same markings. These don't have any markings at all. There is a list of these markings and the actual values, and I'll link that onto the video in the comments below so you can actually look up what these are. But I'll tell you now, the ones that will mark like S1 or O, that's a 1 microhenry. So 2R2 would be a 2.2 microhenry inductor. What goes wrong with inductors when they fail? Well, the honest answer to that really is they don't. Inductors must be just about the most reliable components you're ever going to find on a circuit board. And the main reason for that is really there's very little to go wrong with them. It's just a piece of wire wrapped around a former. So these are some of the surface mount ones that you can see inside. It's just a piece of wire, that's all it is. So there's practically nothing to go wrong with an inductor. There's realistically three ways they could fail. One is physical damage, so the actual former it's wrapped around gets broken or a chunk gets broken off it. But that's visible, you can easily see that sort of damage. And basically that will reduce the inductance because it reduces the amount of magnetic material in the inductor. So the amount of magnetism it can store is reduced and therefore it reduces the inductance. The other thing that can go wrong with them is they could burn out or go open circuit. But to be quite honest, it's more likely for an inductor to go open circuit because where the leg is soldered to the board, the solder joint has gone because of the weight of the component sort of waggling around over the years, especially if it's an item subjected to vibration, you know, something that's portable, for example. So really that's two ways they can fail. The third way is a little bit more obscure and they can actually get shorted turns. I'll just zoom down to show you what I mean. So as you can see, this inductor is just a coil of wire around like a donut shaped former, and although it looks like a piece of copper wire, which it is, it's actually coated with enamel. So if I just get my multimeter onto the bleeper, you can hear it, and I make a contact across the inductor and I read basically a short circuit. It's just a piece of wire. If I try to touch, or if I do touch any of the copper wire in here, look, I don't get a connection, yeah? And that's because it's actually coated with an enamel, so it has an insulator. But it's possible for that insulation to get broken, maybe usually again down to some sort of physical shock, and for two wires, two turns to touch together. Now you might think that, well look, let's look at this piece of wire here. There's like, I don't know, I haven't counted them, 24 turns, 25 turns maybe, I haven't counted them. So if two touch together, you've now got 24 turns, so that wouldn't make any great deal of difference. But in fact, if you have a shorted turn, that turn effectively becomes a secondary winding, which is short circuit. And when it tries to magnetize the coil, it also induces electric current back into that shorted turn, which will pass an infinite amount of current. So it reduces the magnetic field, how much it can magnetize. It reduces the impedance of the inductor. So that's the other way they can fail. If you get an inductor that is smoking or something like that, you can pretty much say it's because there's too much current passing through it. It's not smoking because there's something wrong with the inductor. It's smoking because there's a short circuit on the circuit it's providing, and the power supply coming in is capable of producing a very large amount of current, enough to get the wire so hot it will smoke. So if you see that, and you'll see it on larger inductors with many, many more turns, not things like this, but if you see that, it's a short circuit that's causing it, yeah? The other thing is, in these sort of inductors, you'll find them in VRM circuits. Yeah, another one here. If these are running very hot, but the voltage regulator is working, but the inductors are getting hot, and sometimes they look like these, that is normally because the capacitors on the output side of the coil, the low voltage side, have gone high ESR, and it causes a lot of spikes. So if you find inductors and voltage regulator modules running hot, it's not the inductor, it's the capacitor on the load side, or capacitors on the load side that are faulty. So can we test an inductor? Well, technically speaking, yes, because even with a multimeter, if we take a multimeter and we look at one of these inductors, unsurprisingly, it will look like a short circuit, but it's just a coil of wire, and it'll read short. Yeah, and you can't see any difference. Even this one, which has the most windings in compared to the other ones, you can't see any difference between that inductor and a short circuit. But the only thing you ever likely to see go wrong with an inductor, it goes open circuit. So yes, if it reads open circuit on your meter, it's faulty. But you can't measure an inductor on a multimeter. So can we actually test an inductor with any of our meters? And the answer is yes, we can. One method we can use is an LCR meter. This is an inexpensive LCR meter and component analyzer I bought from AliExpress. It was about €6. It was very cheap. LCR meter stands basically L is inductance, is capacitance, R is resistance. So it means an inductor, capacitor, and resistance meter. And as I say, this also will analyse semiconductors. So here's one of the coils that we looked at earlier, one of the inductors. And let's try to measure it on our LCR meter. So I'll just hold it in place between pins 2 and 4, 2 and 3. Just switch it on, and let's see what it tells us. So that's saying it's 0.3 of an ohms, but more it's saying it's 0.02 millihenries. 1 millihenry is 1,000 microhenries, so that is 20 microhenries. Okay, let's try one of the smaller ones. So this one is marked as 1 or 0, which is actually 1 microhenry, so it's 20 times smaller than this one. Let's see what the meter thinks of this one. So again, we'll hold it in place against the contacts. Let's get it into position. Okay, it's in. Let's try test this one. Let's wait a moment and we'll see. Okay, so now it just tells us that as a resistor, 0.22 ohms. And there seems no way to tell this tester that I want to measure inductance when I'm measuring small inductors. It seems to just refuse to do them. We can try the other one. This is marked R30, which is 0.3 of a microhenry, so it's even smaller inductance. Let's see what the tester thinks of this one. Hopefully I've got a good connection against it. Yeah. Okay, I'm just maybe not making contact. Just one moment, we'll try again. Because the legs are so large, it's very difficult to get them into the tester. Okay, so it says it's 0.21 of an ohm resistor. Again, it's just trying it's a resistor, but we want to measure an inductor, so that's not really handy. It's okay, it seems, with larger inductors, at least 20 microhenries and more, I would assume. I don't know what the upper limit is. But more than likely, if we want to measure an inductor, it's probably one of these. So there is a way we can actually measure them. We'll have a look first. So this is the 1 microhenry inductor. And we'll put it on the ESR meter. This is the ESR meter, okay? We'll switch the ESR meter on, and let's have a look to see what this tells us. So normally this is used to test equivalent serial resistance in capacitors, which it tells us in ohms. So this is actually going to measure this in ohms. Okay, good connection. That's reading 0.631. Okay, 0.631. So I'll just make a note of that one. 0.631 ohms, yeah? Let's have a look at the other little one we have. So let's have a look at the smaller one. This is marked R30. So this is 0.3 of a microhenry. So again, we'll put it on the meter. We'd expect this to read lower. And it reads 0.148. Okay. I'll just make sure the meter is zeroed because we want to get an accurate reading of this. Yes, it's basically reading 0. I'll just press 0. Okay, it's pretty 0. Let's just try it again and see if we get the same reading. 0.166. Okay, so we can make a note of that one. 0.166. And let's also measure this third one. We know this is a 20 microhenry according to the other test meter. What does this one say it is? So again, we'll come on here and we'll measure the resistance. And that's reading 11.1. Okay, 11.1 ohms. So that will give us a resistance, but from that we need to work out what is the inductance. And there's a formula to do this, and I'm just going to show it to you now. The resistance I read of an inductor depends on the frequency of the signal that I'm sending through the inductor. It's actually called reactance, or if you like, inductance. So there is a formula, and the formula is this. The symbol for reactance is XL. But for our purposes, we can call it R, the resistance, okay? And the formula is 2 pi F L, which looks very complicated, but I'm going to make it very simple for you. 2 is number 2, okay? Times, when there's a space, just time check. Pi is a mathematical constant, 3.14, and that's always the same. F is the frequency of the signal in hertz that we're sending through the inductor, and you can see this is a 100 kilohertz in circuit testing. So F is 100 kilohertz, or if you like 100,000 hertz, okay? And L is in henries, yeah? So the resistance will measure that, okay? If you want to know the resistance, you need to know all these, okay? Now, 2 pi F is the same. So basically it's 2 times 3.14, which is 6.28 times 100,000. So 628,000 is that, and that will never change, assuming that the meter is a 100 kilohertz meter. So basically resistance that we read equals 628,000 times the inductance in henries, okay? If you know what the inductance in henries is, you can work out what the resistance should be. So let's have a go at that, and let's see if the ones we measured were actually reading correctly. So the 1 microhenry that was marked 1 or 0 was actually reading 0.631, okay? And I think you can see it's close, yeah? So let's work out the calculation. So if we know the inductance is 1 microhenry, that's 1 millionth of an henry. Well, this is in henry, so we take 0.0000001, okay, it's 1 millionth. And we multiply it by 628,000, 628,000, and it comes to 0.628, and that's almost exactly what we measured, 0.631, okay, in ohms. Okay, so we know that our meter was reading that 1 microhenry coil correctly, yeah? We did the same with this one. This is 0.3 of a microhenry, it's a smaller one. And this one was reading 0.166. Let's see if that was actually correct for the component. Okay, so once again, just clear the data. Can I get rid of it with this thing? Yes, I can. So we want 0.00000. If it was 1, that would be 1 microhenry, but it's a third, so 0.3. Yeah, 0.3 of a microhenry times 628,000. Okay, 0.188. 0.188, okay, and we actually read 0.166, so we were close. On the small one it wasn't quite accurate, and that was a 0.3 microhenries, okay. It was in the ballpark. So what does this one read on our ESR meter, and can we calculate again what the value of it should be using the ESR meter? Yes, we can. So again, we'll take the ESR meter. I already did it anyway. It was 11.1. It was 11.1. We know what it was. Here we go. 11.1. Okay. So now we need a formula to work the opposite way. That if we know what R is, what is L? What is the inductance? I'll show you how to do that one. So the formula here is as simple as that one, yeah? If you remember 628,000, if you've got an ESR meter like this one, you can always do this. Okay, so L. L equals R, the resistance you measured, divided by 628,000. Okay? That's it. So let's work it out on ours. So we know what R was. Let's get the calculator and let's do it again. Make sure I hide that away, shall we? I can't get into my own phone. Okay, I'm in. Okay. So in this case, we know R is 11.1. 11.1 divided by 628,000. 628,000. Okay? And that equals a small number with lots of zeros in it. That is in henries. But we want to know what it is in microhenries. So the easiest way to do that is times it by 1 million. Okay? And it equals 17.68. So that's the actual value of that inductor. And that's how you work them out. So to know the inductance, if you wanted a microhenries, it's the resistance divided by 628,000 times 1 million. Okay? That's your formula. The other one is a bit simpler, 628,000 times L. Yeah. You can, if you want, you could put the L into microhenries, divide it by 1 million, but there you go. Okay, so there we have it. 17.68. What did this say it was? Just remind ourselves. So we take this coil again. We'll stick it onto here. I'm sure it was something similar, but it was. Oh, it was 20. Yeah, this says it's 20. Okay, this said it was 20. 20. Okay. Because the ESR meter was very accurate reading the 1 microhenry, I tend to believe that is the correct one. About 18 microhenries. But they both give us a very similar result. Okay, so that's how you actually work out the inductance of an inductor with an ESR meter. Now I want to just show you one more thing. I mentioned in the video that if you have a shorted turn in an inductor, it decreases the inductance because it acts as a secondary that is short circuit. So what I'm just going to do is now I'm just going to wrap a piece of wire around this inductor, and I'm going to measure the resistance again, on the ESR meter and see what it says. So there is our inductor with a shorted turn on it. Okay, we'll just stick the meter against it and we'll read it. And what do we now have? It's now 7.44. Yeah, wondering why. Let's hold things down. Settled. 7.2. Okay, so the inductance is now actually reading 7.2. Yeah, the resistance. And again, we can just work out what that actually is. We'll do it on the calculator. We'll see how much that piece of wire actually acting as a shorted turn reduce the inductance. Okay, so we'll just remove all this one. It is R 7.2 divided by 628,000 times 1 million. Okay, so it's now gone down to 11. It's gone from 18 to 11 microhenries just by wrapping a bit of wire around it. You saw what I did. I wrapped one bit of wire around it and I connected it into a short circuit. So that, guys, is what happens to an inductor when you have a shorted turn. If this inductor is part of a buck regulator circuit, the buck regulator works by magnetising this core. So it has a FET which turns on and magnetises the core. But before it can fully magnetise and become just a piece of wire, the FET turns off, and then it demagnetises. When the inductor is fully magnetised, that is known as saturated. Okay. If the inductance decreases because of a shorted turn, it will saturate at about 2/3 of the value it would normally saturate at. So at that point, the FET is still turned on. This is now a short circuit and you blow the FET. That's why shorted turns matter. Okay, guys, so I hope you've learned enough there about inductors, all you need to know about inductors to repair stuff. Hope you enjoyed that video, and I'll see you soon on the next one. Adios, amigos.